So one question which is about this Lagrangian and Eulerian description of motion. So what solid mechanics mostly we use is Lagrangian description of motion. So see here what you are doing, you have a body, let us say initially at time t equal to 0, this is its reference configuration. Of course you would be observing this from a reference frame with certain coordinate system. So this is the frame of observation. So what you are doing is that you have some material point in different material points in the body, say some point P, and it has its initial coordinates. So those initial coordinates may like we are also saying say x, y, z. Let me say that these coordinates are x, y, z. So there is a material point here, there is a material point here, there is a material point here. So in Lagrangian description of motion, what we are doing is this is the body at t equal to 0. Then this body deforms and moves and occupies another configuration, say at some time t. And then this material point P, which is here, now it goes to the new location. Let us say that new location is P dash, and then it has its current coordinates. Say let us say I'll say that the current coordinates are small x, y, z, and of course this is small x, y, z are functions of time, and also functions of initial coordinate, because a point which was here will have different current coordinates. A point which was here will have different current coordinates. If you see the current coordinates, these x, y, z, they are functions of their initial coordinate and also time, because the current positions are changing with time. So in this, if you are tracing each and every material point, so if this material point is initially here and then it goes to, let us say, at this particular location, and similarly I have another material point, it goes to this particular location and so on. So every time in Lagrangian description of motion you are tracing all the material points. So you are finding out that a material which was say here in the reference configuration, where it has gone, a material point which was here in the reference configuration, where it has gone. So all the time these current coordinates, the x, y, z are current coordinates, and capital X, Y, Z are, let's say, reference coordinates. So the current coordinates are functions of initial reference coordinates, and these are fixed, because we start with the initial known configuration of the body. So here you will find, say for example, small x is a current coordinate, and that can be written as its initial coordinate x and plus a displacement, which is displacement along the x direction, and this displacement itself would be function of x, y, z and t. Now this x, y, z, they are fixed values, because we are all the time tracing this particular material point which was initially here. So this x, y, z, they are fixed, capital X, Y, Z. So similarly y, you will write that its initial y coordinate plus displacement along the y direction, which is again a function of function, meaning is that for different points it is going to be different, that displacement. So x, y, z and t, and similarly say if you write the z, so that is going to be z plus displacement along the z direction, again function of x, y, z and t. So here if you see, if I want know the velocities, we differentiate these coordinates. When you differentiate, of course these are initially known values, they are not changing with time, because we are starting, these are the starting coordinate values. So these are not changing. So the velocities are x dot is going to be simply derivative of u with respect to time, because again it's also function of initial reference coordinates and time, but these are fixed quantities. So here x dot is equal to basically derivative of u with respect to only t, which is del u by del t, and we usually denote it by u dot, and so on. So we of course refer to the velocity components as u dot rather than using x dot, y dot and z dot. So this is referred to as Lagrangian description of motion, and typically in solid mechanics, because the motions involved are usually of the order of maybe at the most few centimeters and things like that. So you use this description of motion for solids. But when it comes to Eulerian description of motion, so in this what you do is, since the still the Lagrangian description can be used, but the problem with that is because in case of fluid mechanics the displacements involved are of the order of sometimes can be even kilometers and so on. So you cannot really trace the material point that if I at some starting point, if there was a material point here, if I start tracing that material point where it has gone, it would be a tremendous task. So what then you do is, rather than tracing the material point, what you study is you focus within a control volume, and what you then you study is that at some time t, whatever are the material points here, we just look at what are there, what is the pressure at that location, or stresses at that location, or the velocities and accelerations. So in this case, at any given time, these, if I have some material point here, this would be the current coordinate of that material point, because in the next instant this is going to go somewhere else. So right now what I am tracing is the current coordinate of the material point. So then what we do, at any time t, we write the coordinates x, which is a function of, essentially you are saying that this position itself is a function of current coordinates. So like I will have some point here, I will have some point here, some point here, and these are directly the current coordinates. So I will have x, y, z are the current coordinates, and then I describe any other quantity. For example, if I describe the velocity, so velocity would be, let me denote it as now for this case I want to differ from what I use there, u dot. So let us say that I have x component of velocity of a material point which is here. So now this is a function of, because a material point which is here and the current coordinates are x, y and z, and this of course is going to be function of time. So at some other instant, so at t, if I have a material point here that has got this velocity, and which is different, because if I have some another material point at this location, that velocity in general would be different. So what we are trying to say here, that the quantities of interest, say in this case velocity, is a function of current coordinate and time. So now since the current coordinates are going to change, now when you are differentiating this, if I want to get the acceleration, which is basically a derivative of v with respect to time, and when you are now want to get this total derivative, because this x, y, z itself is changing, these are not the initial coordinates, they are the current coordinates. So the current coordinate, initially I have a material point here, this is going to move somewhere else, so its current coordinates are going to change. So that means these current coordinates are functions of time for a particular material particle, although we are not tracing that material particle, but at this instant we are saying that its current coordinates are going to change with time. So when you write this derivative, you would write del Vx by del x, and then derivative of x with respect to time, so that would be dx by dt, and which is basically nothing but Vx itself plus del Vx by del y into dy by dt plus del Vx by del z into dz by dt, and it's also explicit function of time, so you have del Vx by del t. And this is nothing but x component of velocity, so this is Vx, this is Vy, and this is Vz. So now in this case the acceleration, or the time derivative basically, if you look at, has got these three terms, additional terms, they are referred to as convective acceleration term, and this is the material derivative which is coming del Vx by del t. The reason here is that you are not, once the material point goes here, your boundaries of the current control volume are going to be fixed. So while some material point enters here, after some time this goes occupies different locations here within the control volume and then goes out. You are not tracing that. You are all the time studying that if there is some material point at this particular location, what are its velocity, acceleration, stresses experienced by that, or strain rates experienced by this particular material point. So here you find that these derivative terms are additionally there in case of Lagrange Eulerian description of motion. So you are here you are not, important thing is that some material point which was here, you are not bothered when it comes within the control volume. Then you look at at this particular position when this material point is there, what are its all these properties, and then it follows certain path here, and finally it will follow this path till then it occupies some point in the control volume, after that it leaves. So you are not tracing that. So the difference between the two, the Lagrangian description, is that you start with this material point, all the time you are tracing that where that material point has gone. So its identity is, in this case the material point identity is its initial coordinates. So we are saying its current coordinates are functions of initial coordinates and time, and since these are fixed quantities, so the derivative is only with respect to time. Here we are saying that we have some material point at its current location. So our no, here the spatial domain is fixed, whereas in case of Lagrangian description of motion, the way the body moves, here spatial domain is actually moving. Although most of the time when we are doing a small deformation analysis, we are saying that the deformation is actually small, so the current and the deformed configuration is nearly the same for the purpose of writing these equations. So we don't consider, but when we consider large deformation, we consider that. Now here what you are saying, that this is actually fixed, there is no change in this. In this there are certain material points, they enter and then they go out, we don't worry about that. So then the identification of material points here is through their current coordinates, and so their velocities, accelerations are functions of current coordinates and time, so that has to be then taken care in the derivatives. So that is the difference, and that is why I had written the velocity in the last class as just time rate of change of displacement, because displacement itself is a function of initial coordinates and time. Initial coordinates are fixed, whereas in this case no Eulerian description of motion, all the quantities are expressed in terms of current coordinates. So the current coordinates are obviously changing with time, so that when we are trying to find out, say, acceleration like quantity, this no aspect has to be taken into account. Then another question was that when I had discussed one of the application to fluid mechanics problem, there we had said that these velocities are no small, so the convective terms of acceleration be neglected and then only be retained this term. But if these velocities are significant, these terms, no convective acceleration terms are important, then you'll have to consider that. Of course, then the problem becomes nonlinear problem. So this is what we are doing, the difference between the Lagrangian description of motion and Eulerian description of motion. Okay, was there any other? So I think there are other smaller questions, I addressed that. So now next let me, I think I wanted to take Lagrangian, basically the Hamilton's principle and then the equation of motion, but maybe few more elements let us take. So if I consider, say for example, Timasenko beam element, we want to derive the expression for kinetic energy, and let me take the standard one, two-noded Timasenko beam element. So two-noded Timasenko beam element means you have two nodes, the degrees of freedom are, say, V1 here and theta 1 and V2 and theta 2. So if you remember, for this within the element I have this local coordinate, so the displacements were written as u was minus, and the coordinate system is, this is x and this is your y, so u are written as minus y into rotation theta, and this theta is a function of now x and t. So also u is a function of x, y and t. V was taken only a function of x earlier, now it's function of x and t. So this is what we assumed when we discussed about theta is rotation about z axis. This is x, this is y, so theta is the rotation about z axis. Now if you look at the velocities are going to be u dot. Now see here, this x is the initial coordinate of the material point. So when you are differentiating, you are only differentiating with respect to time. So u dot is going to be minus y, that's again initial coordinate, into theta dot. Theta dot meaning is del theta by del t. And v dot is simply going to be, of course, v dot, which is del v by del t. Why I am again writing del v by del t? Because it's also a function of x. So it's a derivative only with respect to t, keeping x same, that is for the same material point. So this becomes del v by del t. With theta dot is also del theta by del t. So if I write kinetic energy T, which is half integration over the total volume, and then u dot is square plus v dot is square, this is the square of the velocity magnitude into differential mass, which is rho, and into dv. And then what you can do is split this volume integral into length and cross-sectional integration. So you can write this as half integration say 0 to L and the integration over cross-sectional area. U dot as you see is minus y theta dot whole square. V dot is of course as it is, we have written there, and then into rho dA dx. dV you are writing as differential cross-sectional area into dx, the way we were actually doing earlier. So now if you look at this, will be integral 0 to L, and the first term is y square into theta dot square. So the integral y square dA will be your Izz, the way we wrote earlier. So the first term would actually become rho into Izz into theta dot square. Second term is simply integral a dA, that will give you a, so it would be rho into a into v dot square into dx. So here what I have done is, ultimately you see this term is referred to as rotary inertia term. It can be similarly taken in case of Euler-Bernoulli beam element. There in place of theta dot you will have actually del 2 v by del x del t. Because rotation is del v by del x, its time derivative would become del 2 v by del x and del t. So this is, once you have this, then rest of the steps are straightforward. Typically what we also do is that since we want to substitute the interpolation in the form of product of matrix and matrices and vectors, you can write this as something like a construct a vector of v dot and theta dot. In between you have this matrix rho a zeros, rho and Izz, and then you have v dot and theta dot dx. This is when you multiply, you are going to get basically the same thing. And why you are doing, so that you have v interpolation for v and theta, you can substitute that directly. So we know that v dot and theta dot, they are going to be, as we have discussed earlier, this is a two noded truss element. We have, for v there are 2 degrees of freedom, for theta also there are 2 degrees of freedom, and from the expression for strain energy we had seen minimum requirement is a linear polynomial. So based on that, the interpolation for v is n1 0, n2 0, 0 n1, 0 n2. Both are interpolated in a similar manner, although if it is used for thin problem, it will lead to locking. So now the time derivatives are going through the degrees of freedom. So now here this v1 theta 1, v2 theta 2, they are functions of time. So you will have v1 dot, theta 1 dot, v2 dot and theta 2 dot, the way we did earlier. And so what you call this as H interpolation matrix, and this as dE dot. I think earlier maybe yesterday I started using superscript, I was using actually this as subscript. Anyway, it doesn't matter as long as you are consistent. So then finally you can see that kinetic energy T would be half, the same straightforward essentially procedure. So it can be written as, I am not repeating in between steps, you substitute it here and then take out d dot transpose to the left and d dot to the right, do the integration. So you will get this as d dot transpose into ME mass matrix, element level mass matrix into dE dot. So this is what finally your kinetic energy would be, and in this case ME is going to be integration 0 to L, and then you have H transpose, and in between this rho a 0, 0 rho and Izz coming directly from here this expression and into H dx. So this will be mass matrix. Actually you can, the H here, n1 n2 are the same shape functions. N1 is 1 minus x by L and n2 is x by L. So you can do the integration and finally get this matrix. So that step I will leave it to you, but since these are same interpolation functions, you will find that when you do this multiplication and carry out the integration, you will find that this will be consistent mass matrix would be involving V, it is going to be like rho a L by 3 0, rho a L by 6 0. So if you multiply, do the integration, this is what you will get. You can cross check that. And same thing for the other degree of freedom, that is rho Izz into L by 3 0, rho into Izz into L by 6. Then this would be again rho a L by 6 0, rho a L by 3 0. That's just the multiplication and integration. So finally 0, rho izz into L by 6 0 rho into izz L by 3. So this will be your finally mass matrix. So you will see it is quite similar to what we did actually for the truss problem, because the shape functions are now same as what we use in case of a truss problem. So this is the mass matrix for a Timasenko beam element with a standard interpolation. Of course, if you are using consistent interpolation, then H matrix is going to change, and therefore this mass matrix will change. If you are using interdependent interpolation function, then also accordingly as per the shape functions there would be change in the mass matrix. The format would be same. Now if you look at, say for example, also want to look at plane stress or plane strain element. So there are 4 noded or 8 noded, of course that you can always do in a similar manner. So here what we are doing is that in the physical coordinate space we have this element, let us say 4 noded element, these are the coordinates x, y, and then this is mapped to the natural coordinate space as a square xi and eta. So in this case if you look at the velocity and then the kinetic energy, so since we are saying that any point here has a displacement along x direction as u and the displacement along y direction as v, so you can write kinetic energy half integration again over volume, and there are only 2 components of displacement, so 2 components of corresponding velocities, so u dot square plus v dot square, and then you have rho into dv. So there is no displacement in the z direction. So now what we want to do is finally we want to write it in terms of shape functions and the final expression for this kinetic energy. So you can split again this, because u dot and v dot they are only functions of x, y and of course time. So I can split this integral into area integration over x and y and thickness integration. So thickness integration, because none of these quantities are functions of thickness or coordinates, you can say that thickness integration is either minus h by 2 to plus h by 2 towards 0 to h finally will just give you h. So I can write this as u dot square plus v dot square into rho into h into dx into dy. So dv is written as h into dx into dy. This is directly written because u v are only functions of x and y and also time, but not function of z. Now see, this can be written as same way double integral. I can write rho h, you can write anywhere. If it is a function of x and y, you have to keep it inside integration. If it is independent, you can take it out. And then this term again can be written as u dot v dot transpose into u dot v dot, and then you have here dx dy. So it will give you the same thing, and why we want to write in this fashion, so that we can bring in our interpolation matrix H. So again the u dot and v dot is going to be same way, the way we have done for the static problems, that this is going to be n1 0 n2 and so on. So we will have here H matrix and into dE dot. So if you finally substitute it here, half will be there, so this is half here, half here. So finally you would see that you can again you substitute this back here, and d dot transpose left side, d dot on the right hand side. If you take whatever in between, you get is your mass matrix. So you will see again this is half of dE dot transpose into ME, element level mass matrix, into dE dot, where now your this element level mass matrix ME would be now integration over a rho into H into H transpose into H into dx dy. And since this is isoparametric formulation, so finally we write this because H is going to be in terms of xi and eta natural coordinates. So you can write this integral in the natural coordinate -1 to +1, the way we did earlier, and the H the quantities which are integrated are already function of xi and eta. This dx dy is determinant j times d xi and d eta. And this can further be written in terms of Gauss quadrature numerical integration, summation over I equal to 1 to n, j equal to 1 to n, and then rho into h H transpose into H into J, this whole thing evaluated at xi I eta j into Wi into Wj. So this is, you would find that once we understand the formulation of the elements for static problems, so finding out the expression for mass matrix and therefore kinetic energy is actually straightforward. So we are just writing the kinetic energy. Of course, see, this equations of motion can also be derived directly starting with the differential equation, writing the Bettel residual statement big form, and then following that procedure. So here we are writing in terms of kinetic energy. So once we have this kinetic energy, which is the additional quantity coming in case of dynamic problems, we can derive the equations of motion. So that's the next step. Earlier we were calling them as equations of equilibrium, now equations of motion. So I am assuming that you have some background about Hamilton's principle, otherwise you do a self reading about it. So I am going to use, since we are talking in terms of energies, we can use Hamilton's principle. So I am going to use here Hamilton's principle for the derivation of the equations of motion. And what this Hamilton's principle states is that I am trying to study the motion of a body between two time instances, one is t1, another is t2. So if I construct one integral from t1 to t2, and the integrand here is the first variation in kinetic energy minus first variation in the potential energy of the conservative force field acting on the body plus virtual work of non-conservative forces. So if I take this and integrate it from t1 to t2, this should be equal to 0 for arbitrary variation in the motion of the body from t1 to t2. But that t1 and t2 we are assuming that the configuration of the body is known. So at those two time instances, the variation in the motion variables, in this case a vector of elemental degrees of freedom, would actually be 0. So this we call as Hamilton's principle. So if the actual motion of the body will be governed by this equation, wherein delta t, this is first variation in kinetic energy Ke, and delta V is the first variation in potential energy of conservative force fields. Means the forces can be internal or external, conservative force fields, and this delta WNC is virtual work of non-conservative forces. So time dependent forces are actually always referred to as non-conservative forces, although their curl might be a null vector. So conservative force field means if you have the force which is a function of only position and its curl is 0, then you call that force field as conservative force field. And so if time dependent forces are always referred to as non-conservative forces or force fields. So now if I want to look at the problem what we are considering, so see we have expression for t already, which for any general case we can always write it in terms of vector of elemental velocity and mass matrix. So d transpose into me into dE. Of course we are assuming that there are no inertia nonlinearities. So now if you want to find out first variation, that is delta of t, that would be half the and the variation is with respect to unknown quantities. Here the unknown quantities are basically your vector of elemental degrees of freedom, and then finally the corresponding velocities. So this is half of delta dE dot transpose into me into dE dot. So I am using product rule. So since we want to take the variation of this, so variation of the first term into rest of the things plus half into dE dot transpose into ME into now the variation of the second, which is no dE dot itself, this side. So here I have put variation with the first plus here variation with the second term, because variation is with respect to unknown quantity, which is dE, function of time. So the variation is going with dE dot. Now if you look at individually, these are scalar quantities. This whole thing is a one single number. When you multiply all three together, mass matrix and the transpose of dE dot and dE dot this side. So as far as this is concerned, I can replace this by its transpose. So I can always put here transpose of this. Because this is scalar quantity, it doesn't finally change anything. And if you now open this transpose, this will come first. So you will have again delta of D dot transpose, and then you will have ME transpose, since ME is symmetric, so that would be equal to ME, and D dot transpose would become DE dot. So then this term and this term would be similar. So then you can write this as because then half of will go when you add them. So you get delta of dE dot transpose into ME into dE dot. So this is your delta T. The first variation in kinetic energy is given by this. So what we have is here left side delta dE transpose, that is this is variation in elemental velocity, and this is the velocity itself, velocity vector, and this is the mass matrix. So this is variation in T, that is kinetic energy. Now if you look at the other part, this is straightforward, similar to what we did earlier, the variation of total potential energy. The other part is this V and W virtual work of non-conservative forces. So we have actually, for static problem, we have already talked about I. So I, we were all the time saying that half of dE transpose into KE into dE, and then of course we were also having this external forces and internal forces. So we were saying D transpose into F external for the element. So since I am using this superscript, let me just slightly change this, and minus also D transpose, there is a minus here into, then we had F internal for the element. So let me, okay. So this is what we wrote earlier. So this can always be written, as long as the problem is a linear problem, we can write the total potential energy expression I like this. But since here these forces are explicit functions, in general these forces are explicit functions of time. So what we do is, now we cannot club this under potential of conservative forces. The moment the forces are no time dependent or velocity dependent, they are non-conservative forces. Although if you treat them as the whole thing as V and W and C you take as 0, still the equation will turn out to be same, but it's not actually consistent with what this Hamilton's principle states, that what we should have here is only the potential energy of conservative forces, and this is the potential virtual work of non-conservative forces. So what you can do is, if you write delta I in a similar logic, you can write it as delta of dE transpose. We have done this earlier, KE into dE. So two terms, and then no second term you write replace by its transpose. So from the first, finally you are going to get this, and these terms what you get is simply this is delta of dE transpose into F external and minus delta of dE transpose into F internal. Now this part, the one which is coming from strain energy, this is actually we call it as delta V. Strain energy is although stresses, displacements, so therefore strains, stresses, they are implicit function of time, but directly they are in terms of U, V and W. So and their gradients. So we call this as essentially we can put this under variation of potential energy of conservative forces, and the other part, this I can put as plus virtual work of non-conservative forces. So since I am writing in terms of work, let me not put a minus sign here. I'll minus sign with the virtual work. So I'll put minus delta W and C. So where delta V is delta of D is the same thing, D transpose into KE into DE, and delta WNC is, now this whole thing I am calling it as delta WNC, so delta of D transpose, and let me write both of these together. So F external for the element and plus F internal for the element. So what I am saying, whatever term we are getting in the earlier in case of static problems, whatever we called as total potential energy, now out of that this is the potential of conservative force field, and this is the out of that this is the contribution due to non-conservative forces, because particularly this is explicit function of time, so we cannot call it as as a conservative force field. So once you have this, now we have the expression for, keep in mind that in place of delta V, if you substitute this also, final equation of motion is going to be same, but as I said, that's not a consistent way, because we have only in delta V we should have only the variation of potential energy of conservative forces. So now if once you substitute this expression for delta T, this expression for delta V, and this expression for delta WNC, you can finally get your equations of motion. So again, going back to Hamilton's principle, I have T1 to T2. First is delta T, the variation in kinetic energy, which is delta of delta of dE dot transpose into ME into dE. So that this is the first term. We are going to integrate this whole thing minus delta V, which is delta of dE transpose into KE. See, the actually the derivation itself is straightforward. So that's the delta V part, and this is the virtual work of non-conservative forces. So there is no minus sign here, because I am not writing the potential but the work itself. So that minus sign, I have just left it there. So delta WNC is just these two quantities. So I have plus delta of dE transpose, and then I can put these two together. So you have F external for the element and plus F internal for the element, and this whole thing is integrated with respect to time and equated to 0. That's coming from the Hamilton's principle. Now here, as usual, earlier we used to do, so we wanted to say there that delta D is arbitrary quantity, so this integral should be 0 for different variations in dE. So but here only problem is that this is D dot here, I'm sorry, I just missed it, so I hope so okay. So now only problem here is, if you look at this is variation in, right now the variation in elemental velocity vector, whereas this is the variation in elemental degrees of freedom. So what we want to do, since independent variation is only variation of the elemental degrees of freedom, which is of course function of time, and then by differentiating the actually variation of delta dE, we get the delta dE dot. So this is actually d by dt of because the variation and time derivative are interchangeable. So that is delta of actually dE dot can be written as d by dt of delta dE. So essentially this is not an independent variation of elemental velocity vector, but is just the derivative of variation of elemental degrees of freedom vector. So at this stage we cannot conclude about what should be the equation governing rest of the terms what are present here. So for the first term, what we do is we do the integration by parts to transfer derivative from the variation term to the other term. So when we do the integration by parts, keeping this as the first term, so you will get delta of dE transpose into ME into dE dot, and this whole thing evaluated at T1 and T2, that's the limit part, then minus, and you will have integration then T1 to T2. Now the integration of the first term, which is delta of now dE dot, so dot would go, so this simply will become delta of dE transpose, and then the derivative of the rest of the terms, that is derivatives of this product. Since this is independent of time, so the derivative would be only of this. So this becomes me into dE double dot now, because already one time derivative is present there. So this is what you get when you do the integration by parts for the first term dt here, and then of course the rest of the terms. So the rest of the terms are no, that minus no, again of course the integral here I separated out, so you can write it as t1 to t2 and then delta of dE transpose into ke into dE dt. Someone or the other is keep opening this door. Delta of d transpose into, you have no f external and plus I'm no one to just write it no, like that dt. This is equal to 0. So now what we have is, one is this expression which is to be evaluated at time instant t1 and t2. Now the condition on delta d we are putting that we know there is no change is possible in d, virtual change is possible in d at t1 and t2. So these are two configurations of the body which are known to us, so we cannot vary those known configurations. So we are going to say that this term is equal to 0 at t1 and t2, therefore this whole expression is 0. The first integral, no, this boundary term, boundary means no, that at time instances t1 and t2, since this is 0, there cannot be any variation in dE at t1 and t2. We are saying that no, we know the configuration at t1 and t2, so this term should be 0. Then what we are left with is actually this. Now in this, in all the terms you will find that there is a delta dE transpose, delta dE transpose, there is a delta dE transpose. So now after putting this delta of d transpose equal to 0 at t1 and t2, I have left with this, which again I can write it as, say, integral from t1 to t2, maybe whole thing you can multiply by a minus sign, then you have delta of dE transpose, and then what you will have now inside is this me into dE double dot, that's this term, then again this plus, you will have this ke into dE, since we multiplied with a minus sign, so I will have minus f external and minus f internal, so then this bracket here, and then dt is equal to 0. So this is what we have. Now what we want is, for any arbitrary delta d, this quantity must be, this integral must be 0, and if this has to be 0 for any arbitrary delta d vector, then that means this integrand has to be 0, and the integrand would be 0 for arbitrary delta d if this expression is equal to null vector. So finally, for this to be for arbitrary delta of dE, we should have me into dE double dot plus ke into dE minus f external minus f internal equal to a null vector. So if you take them to the right hand side, you can say f external and plus f internal. Okay. So this is what you call as equation of motion. So as such the derivation is actually straightforward, but only the steps what you have and the understanding of those steps. So one particular thing is the integration of this term, because only independent variation is of dE. So delta of dE is dot is actually just the time rate of change of that. So we need to do the integration by parts, so that we have everything in the integration in terms of delta dE, this term 0, because we are saying that we know the configuration of the system at t1 and t2. So usually you might, if you want to relate it with physical reality, so usually what you have is, you have what is known as initial conditions or initial configuration of the system. So definitely you know the initial configuration of the system or the starting configuration of the system. So that means at t1 here, For example, when we are saying that no, at T1 we know DE, so there is variation in that has to be 0 because it's a known configuration. But what about T2? T2 is a some other time after T1, and that instant you really don't know what is the configuration. When you solve this initial value problem, reach to T2, then only you know what that T2 is. But here the assumption is that that configuration is also a fixed configuration, whatever it is. So we are assuming that we always all the time know two configurations of the body, and then this integration is between that, and the variation of DE is 0 at T1 as well as at T2. So maybe you can think of the whole thing is kind of periodic system. So you T1 is, so you take a loop and come back to the same location. So T2 equal to T1 where the configuration is known. So you start from wherever you start, you come back to that, and in that context you can say that you know the configuration of the system at T1 as well as you know the configuration of the system at T2. But for the purpose of developing this equation, we are saying that we know DE at two time instances T1 and T2. But most of the time problems we solve, we start with an initial configuration. So that is what we know. And if we solve up to T2, we will get some configuration of the system at that time instant. But that's an assumption here. Of course, T2 need not be ultimately limited to the window of your interest. So you might integrate these equations starting with some initial time instant to a certain time instant. That need not be your T2. T2 can be further beyond. You are only integrating these equations of motion to the time of interest. But the T2 is something where you again know the configuration of the system. So once you actually have this equation of motion, so only say if you compare, we already had these terms earlier for the equilibrium problems. Now additionally we have added this. So this is the restoring force. Now this is the inertia force. Mass matrix into acceleration vector is going to give you inertia force. So what you are saying is that inertia force plus restoring force is equal to all the forces externally applied and the internal forces from the surrounding elements. Sum of these two forces must be equal to the inertia plus the restoring forces. Now there is a question about damping, so I think I am going to stop here and we'll continue. We'll take some examples and then free vibration, harmonic response, direct time integration and so on. We'll discuss that. So there was a question about damping. So how do we incorporate damping here? So far only we included the inertia forces, kinetic energy, corresponding strain energy coming through the delta V, and the virtual work of non-conservative forces coming here. But then if we have damping, how do we model that damping? So one of the popular model of modeling damping is known as Rayleigh proportional damping model. So what you do in this, you say that Rayleigh proportional damping model. In this, what you say, rather than separately bringing in another energy term or maybe through the virtual work of non-conservative forces and then bringing in this equation, once we have this equation, then we say that element level damping matrix, and so also at the global level would be linear combination of mass properties of the system and stiffness properties of the system. So maybe some coefficient, say alpha times mass matrix of the element plus beta times stiffness matrix of the element, where alpha and beta are the constants usually determined based on the experimental data on damping. So if you do experimental determination of damping factor, and then you can actually find out this alpha and beta in terms of that. So this is usually what you do. Of course, if there is some mechanism present in the system, that can be modeled through the virtual work of non-conservative forces. Damping forces are going to be non-conservative forces because they are velocity dependent in general. They can be of course other types as well. So you will include through the WNC, and you can bring those contribution to damping. But most of the time here there is no explicit mechanism present for introducing damping. There can be due to the maybe internal friction in the system, or maybe the air resistance, or even maybe some thermal dissipation. So all of that can be modeled through this Rayleigh proportional damping. This is obviously a model which is an approximation, but for many of the structural systems, this gives you fairly accurate results with appropriate alpha and beta values. determined from experimental data. So this is how you model damping, and if you include the damping, so for the damped case the equation of motion would translate to me into dE double dot plus then the this is inertia force, so the damping forces are going to be CE into dE dot and plus of course then the restoring force KE into dE is equal to F external for the element plus F internal for the element. So this is the only change that if you incorporate damping, this is what you get, the additional term which you call as damping force. So this is with the modeling of damping. So rest of these steps, again you have to discretize a given structure into a number of elements, assemble all the element level equations, and then impose the boundary conditions. So finally you get the reduced system of equation which would be governing the unknown displacements of your nodal points. And then you can using this equation you can do the free vibration analysis, find out natural frequencies, mode shapes, you can do harmonic analysis, frequency response, you can do the transient analysis by integrating these equations of motion. So we'll continue in the next class. If you have any doubts and questions, you can ask outside.